If the human heart stops beating, the body dies. If a car engine seizes on the highway, you crash. So when headlines broke recently declaring that the Earth's inner core had stopped spinning and may have even begun moving backwards, it wasn't just a scientific curiosity. It felt like a warning. Deep beneath our feet, thousands of miles down, lies a solid metal sphere almost the size of the moon. It is the engine room of our planet. Its intense heat drives the churning mantle that moves continents. Its rotation generates the magnetic shield that protects our atmosphere from being stripped away by solar winds. Without it, Earth would look a lot less like a blue marble and a lot more like Mars, dead, cold, and barren. So when a team of geophysicists at Peking University analyzed seismic waves from the last 60 years and concluded that this engine had ground to a halt around 2009, the implications seemed terrifying. Had the engine failed? Was the magnetic field about to collapse? Or was something else? Something far more cyclical and strange happening in the dark. To understand why the core stopped and what it means for the future of life on the surface, we have to solve a mystery that has plagued scientists for over a century. Because the truly scary part isn't that the core is changing. The scary part is how we found out. We cannot see it, we cannot touch it, and we certainly cannot go there. Consider this: humanity has sent probes into interstellar space. We have mapped the surface of Mars in higher resolution than our own ocean floors. Yet the deepest hole we have ever dug, the Kola super deep borehole in Russia, only reached about 12 kilometers down. That is barely 0.2% of the way to the center. If Earth were an apple, we haven't even broken the skin. Everything we know about the world beneath us is effectively a ghost story. We rely on echoes, vibrations, and mathematical shadows to reconstruct the monster in the basement. The first clue that something massive was hiding down there didn't come from drilling, but from weighing the world. By the late 19th century, physicists had a problem. They calculated the average density of the Earth and found it was about 5.5 grams per cubic centimeter. But the rocks on the surface, granite, limestone, sandstone, were only half that density. The math didn't add up. If the surface was light, something in the center had to be incredibly heavy to balance the scale. In 1886, German physicist Emil Wiechert proposed the solution. He looked to the stars for answers. He knew that meteorites were often made of dense iron and nickel. He reasoned that if Earth formed from the same primordial debris as those meteors, all that heavy iron must have sunk to the middle when the planet was young and molten. There had to be a core, a massive iron heart. But knowing it's there and proving it's there are two different things. You can't X-ray a planet, but as it turns out, the planet X-rays itself. Every time an earthquake strikes, it rings the Earth like a bell. Massive amounts of energy radiate outward in the form of seismic waves. These waves are the only messengers we have from the deep. By listening to how they travel, and more importantly, where they stop, we can map the unseen. This is where the detective work gets brilliant. There are two main types of seismic waves you need to know about: P waves and S waves. P waves are fast. They compress matter like a slinky, pushing through solids and liquids alike. S waves are slower. They move side to side like a snake. But here is the key: S waves cannot travel through liquid. The energy simply dissipates. In the early 20th century, scientists noticed that when a massive earthquake hit, the S waves would travel through the Earth, but then suddenly vanish. They never showed up on seismographs on the other side of the planet. Something was blocking them. This shadow zone was the smoking gun. It proved that the Earth wasn't solid rock all the way down. There was a layer of liquid deep inside, a molten outer core that was killing the S waves. For decades, that was the accepted model. A rocky mantle surrounding a molten core. It was simple. It was elegant, and it was wrong. The correction came from a Danish seismologist named Inge Lehmann. In 1929, she was poring over data from a New Zealand earthquake. She was looking at the P waves, the ones that can travel through liquid. According to the laws of physics, when these waves hit the liquid core, they should bend or refract, creating a specific shadow zone where no waves should be detected. But Lehmann found something that shouldn't exist. Weak, faint P waves were showing up inside the shadow zone. It was a glitch in the matrix. The only way these waves could end up there is if they had bounced off something inside the liquid. She proposed a radical idea. The core wasn't just a ball of liquid. Suspended in the center of that fiery ocean was a solid inner sphere, a planet within a planet. This solid solid inner core is a crushing environment. The pressure is so intense that even though the temperature is nearly 6,000 degrees Celsius, hotter than the surface of the sun, the iron cannot melt. It is forced into a solid crystal lattice. This discovery changed everything, because if you have a solid ball floating inside a liquid shell, nothing is holding it in place. It is untethered. It can move. It can spin. And this brings us back to the terrifying headlines of 2023. For years, the prevailing theory was that the inner core rotated faster than the rest of the planet. It was super rotating, driven by the magnetic torque of the outer core. We confirm this by looking at earthquake doublets. Twin earthquakes that happen in the exact same location, but years apart. If the Earth was static inside, the seismic waves from the second quake should look exactly like the first. They should travel the same path and take the same amount of time. But they didn't. The waves from later earthquakes arrived faster. The path had changed. The only explanation was that the inner core had rotated, changing the alignment of its iron crystals relative to the path of the wave. It seemed settled. The core spins faster, but then the data started to get messy. Around 2009, those differences in wave arrival times disappeared. The waves from new earthquakes looked exactly like the old ones. The changes had stopped. This is what led to the report that the core had paused. But then even stranger data emerged. The discrepancies started reappearing, but in the opposite pattern. The core hadn't just stopped. It appeared to be reversing. Now, before you start building a bunker, we need to clarify what reversing means. The inner core isn't actually spinning backward like a top that's been flicked the wrong way. It's all about relativity. Imagine you're on a highway driving a car at 60 miles per hour. There is a bus next to you in the slow lane doing 50. To you, the bus looks like it's moving backward. If the bus speeds up to 60, it looks like it's standing still. If it hits 70, it moves forward. The Earth's surface is the car. The inner core is the bus. They are both spinning to the east. But for decades, the inner core was spinning slightly faster than the surface. Now, it has slowed down. It is lagging behind the rotation of the crust. So to our instruments, it looks like it's moving backward. But why? Why does the engine of our world speed up and slow down? The leading theory is a cosmic tug of war. The liquid outer core generates the magnetic field, which drags the inner core and tries to spin it up. But the massive rocky mantle above has its own immense gravitational field, which creates friction and tries to slow it down. These two titanic forces, magnetic torque versus gravitational coupling, are fighting for control of the core. And it seems that every 35 years or so, one side gains the upper hand. The recent study suggests this is a roughly 70-year cycle. The core speeds up, spins faster than the surface for a few decades, slows down to a halt, lags behind, and then speeds up again. The last time it switched direction was likely in the early 1970s. Before that, the 1940s. We are just living through the latest turn of the wheel, so the core hasn't broken. It's just breathing. But that doesn't mean the consequences are zero. This deep oscillation is linked to things we actually feel. When the core slows down, the conservation of angular momentum means the rest of the Earth speeds up slightly to compensate. This actually shortens the length of our days by a tiny fraction of a millisecond. It affects the precise navigation of satellites. More strangely, these 70-year cycles seem to line up with fluctuations in Earth's magnetic field and even subtle shifts in the global climate and sea levels. It suggests that the solid ball 3,000 miles down is intimately connected to the atmosphere we breathe. We tend to think of the Earth as a rock, stable, unchanging, and solid. But the reality is that we are living on a dynamic, shifting puzzle. The ground beneath us is drifting, the magnetic field is wandering, and the heart of the planet is swinging back and forth in a rhythm that spans a human lifetime. We are only just beginning to hear the music of this deep Earth cycle. The headlines might have been scary, screaming about a stopped core, but the truth is actually more beautiful. The Earth isn't dying. It has a pulse, and right now, we are just feeling it skip a beat. There is still so much we don't know. We are trying to read the history of a burning sphere using nothing but echoes. But every earthquake, every anomaly, and every reversed spin brings us one step closer to understanding the machine that keeps us all alive. If you found this investigation into the deep Earth fascinating, make sure you're subscribed so you don't miss our next journey into the unknown. And I want to hear your take. Does knowing the ground beneath you is this active make you marvel at the planet, or does it make you just a little bit anxious? Leave a comment below. I read as many as I can. Thanks for watching.